Right, we have a question from your friends from Aizat FP18038. He asks if the engineering assumption for the fluid based on the viscosity, right? So its constant fluid is only for Newtonian fluid. Actually, it depends. Um, but in most cases, in our course, we're going to assume that the fluid, the viscosity of the fluid in the problem that we are solving are constant. For example, we can assume that the kinematic viscosity of water at atmospheric pressure will be at room temperature 20 degrees Celsius, for example. The value is about 1.002 times 10 to minus of 4. Now we're going to look at the pressure drop differences in the quiz, right? And in order for us to evaluate the pressure differences, it's better for us to look at the basics theory about pressure, and we will consider a point in the fluid. So we're going to look at the pressure measuring instrument first. So pressure at the point can be measured using different measuring devices. We want to measure the absolute pressure, we can use the barometers. So the barometers have only one um, tubing there, you can see from the figures, right? And it will give directly the surrounding absolute pressure. And if we want to apply these parameters to the uh, certain engineering problems, what we can do is to connecting the tubes. For example, in this case, the um, from the piezo meters to the barometers, so that one should give you the pressure of air inside the tube that been compressed by the fluid that pushing the compressing the air inside the tube, right? So it will give you the value of pressure there. Yeah. So this is not actually a very good way to do measurement, but actually work should work to give you measurement, right? Another one we have the scale pressure, gauge pressure gauge, and you can find typical application of this pressure gauge when you want to inflate a tire, a car tire, car wheel, right? So the gauge pressure give you the values from 0 but and greater is should be greater than the surround local atmospheric pressure. So the lowest value will be 0, and that correspond to uh, 0 gauge pressure for atmospheric uh, pressure, right? So if we place the gauge pressure gauge mid tubing from the gauge pressure gauge up to the exit of the tube, it will give you the pressure there, right? So normally if we have a flow in the tube, a flow in the pipe, the pressure at the exit will be higher than the atmospheric pressure at the exit. Then we have this vacuum pressure gauge. So it measures the absolute pressures, and this absolute pressure is lower than the local atmospheric pressure. One of the differences between others pressure gauge is that the resolution here is lower than have a negative value. Yeah? So let's say we have a container there, closed container, and then we um, um, exhaust some of the air from the container and produce uh, the space which has a low pressure, and we can use the vacuum pressure gauge to get information about the absolute pressure inside that. So this air pressure system can be used to, yes. So this is the, if we enlarge the photo of the pressure gauge, we can see that the values on the gauge is has less than 0, right? And 0 it will be the local surrounding pressure. And for this gauge, actually can do both, right? The gauge pressure and vacuum pressure as well. But if we have the application that the pressure is lower than the pressure, so we can use the one at the negative values. Now, this also gives you the static pressure, what we call as a static pressure inside the container, right? It means that the air is static, right? So air is static, so we have a static pressure. Especially we can use it for the container or reservoir, right? Something like that. Now we're going to look at the pressure at a point. So this is a representation of the way to show the pressure at a point. Um, in fluid medium, right? So we have the origin uh, of the arrow, right? Having the same length of the arrow, and we have the directions of the arrow. So what we can say that this pressure does not represent a vector, because the vector normally acting in only one direction, but for pressure at a point, it's always towards the particles, and it's covering the whole surface on the point. So we can conclude that the pressure is not a vector quantity. And we can say that the pressure is a scalar quantity. Now we have to think about why we would like to represent the pressure that acting normal to the surface of the body, right? It is the reason. It is because the pressure actually is a variable that can be used to determine the surface forces. So one of the application is that let's say we have a piston, uh, and then we have a single vector force acting on it. Let's say this the upper surface is like having a needle type force that acting on the point, and this force is compressing the fluid bellowing it, right? So normally pressure is represented and pointing in the direction normal to the force, uh, that single unit force. So this is the reason why um, we normally represented the pressure with arrows, and it's always point, and the tip of the arrows is pointing to the surface. And this surface forces due to pressure has a definition, which is pressure times the cross-sectional area at which this pressure is acting. Right? Right. So that's why on the point we can see that the direction of pressure is always acting towards the point. Now, it's better for us to look at the uh, category of force that we're going to learn in this course, right? So for fluid particles, they are subjected to a total force, which comprise the body forces and surface forces, right? So just now we look at the shear stress that create the shear force, and then now we look at the another surface force due to the pressure, right? So this equation, this term actually is part of Newton's second law, and this second law represents the conservation of linear momentum, right? So what does it mean? That if the body is moving at constant speed, it will remain moving at a speed unless there is a net force acting on it. Or if the body is at rest or stationary, it will remain there until there is a net force acting on it. Right? For particle, we will consider only the contribution from these two category of force, which is body forces and surface forces. And this net forces is part of what we call as an equation of motion, right? It can be called linear apa ni, momentum equation. It can be called force mass acceleration relationship, as what we learned in dynamics. So example of body forces is weight, right? Weight also have weight. We know the density and we know the volume of the fluid, then we can get weight, the mass, and then we connect it back with the gravitational acceleration. So this is the definition of the body forces. So we have the mass of the fluid times the gravitational acceleration. Now we can consider a representation of a fluid body, a body of fluid subjected to the um, surface forces and body forces. In this case, we can have two situations. The first one we consider the absolute pressure, and the other is without the atmospheric pressure. And we have uh, the surface force due to the pressure, and the body forces is due to uh, weight. And we represent the schematics here as a control uh, volume in 2D, or control surface, which we control mass, right? In thermodynamic, we call it a closed thermodynamic system. So this term are interchangeably used between the in thermodynamics and in dynamics, as well as in dispute mechanics.